Okay, so this is going to be a quick overview of, or just demonstrating my interpreter and my compiler. So let's start off with the interpreter. Here's the code for it. It has a traversing function that goes through each of the commands. And yeah, so I will just demonstrate this is working. Let's start out with, I have quite a few test files you can see along here, which are I should just use to try cover as wide range of like functionality as possible to try and spot any errors. So this is just a basic one. This is 2, a equals 2, b equals 3, a equals a plus b. So this should output 5. Okay, so just compile. These warnings here are generated from the Lexron parser, and then this warning here, the only parameter here is because I didn't manage to finish implementing the built-in function, so this is just a warning saying that this variable isn't used. Yeah. Okay, and then so interpreter, and then I want to pass in basic2.c, and as you can see, this exits with code 5. Here is a printout of the frame, just the first frame of the function. It's useful for debugging, so I just see what is left over at the end. This is a pointer to a memory location, that's why it's such a large, well, small value. Okay, so now onto branch 1. So a equals 0, c equals 100. Here, this is to test to see if the scoping works correctly, as this should create a new c and not overwrite this value here. So let's try it with this one. Branch. Oh, that's not right. And as you see, it exits with a code 100. So it's not taking on this value, it's ignoring it, even though a plus 1 equals 1 is true. Okay, now factorial, this is to test the recursion to make sure that works. So this is just going to calculate 10 factorial, which, just to make sure I get it correctly, 10 factorial is this number here, and there you go. What's that? Cool. And then this is one of the most complicated tests I have, and it seems to cover quite a wide range of features here. Well, no, yeah, just it's quite complicated, this one, and I was kind of a struggle to figure out what the output should actually be. So function f is just a variable that calls get func, which gets a function with the value of 1. So it defines the variable a, defines another function, variable f, function. If a is equal to 0, it will run this code, otherwise it will run this code. And either one, it will set f, it will define a new function and set f equal to that function. So since our x is equal to 0, x is equal to 1, it should do this code here. So it defines get func2, b is equal to 1, then g is just returns a minus b and returns g. So f is equal to get func2, call f, which should return g, which then sets f here equal to g, and then calls f finally. So we should get an output of a minus b, which is 4 minus 1. So let's hit test, flex, scope 5, and I have an output of 3. And then if I change this around, so this was 0 instead, we should have an output of a plus b, which is 4. No, not sorry, which is 6, which is 4 plus 2, sorry. As you can see, 6. Just set that back. Okay, so that's demonstration for the interpreter. There is more. There is also, I will just do loop 2. just to demonstrate the while loop. Loop2.c. So your output's 20, x equals 10, pass 10 equal into loop, while true, x does not equal 20, x equals x plus 1, else break. And this here was to test if the break functionality was working. Because if it did not break, it would -1 from x and keep going. Well, if it just kept going, it would keep going on infinitely. And this was also to test the return, making sure the returning is correct, so it didn't change x after, didn't keep on executing code once it had finished. As you can see, output of 20, which is correct. Okay, now moving on to the TAC and the toAssembly. So this is an entirely separate program to the interpreter. These TAC and toAssembly are one program, and then the interpreter is another. This just made naming things a bit easier. So if I start out with just, actually, you should be able to see the TAC. Okay, so we start with basics 2. Instead, this uses assembly. Okay, and you can see this is the TAC outputted from here. So you can see this roughly translates declare. This means declare A equal to declare B equal to 3, and then same goes on here. Return value equals to A, return. And then this is then taken by toAssembly here and generates this code here. So it defines these, which are spaces used for functions, really. So arguments used for putting for storing parameters, storing arguments for functions, which then can be used inside the function. Function definition is used for storing the address of the address in the instructions for a function. Closure is used for storing two different parts of data: the address of the data addressing data that it needs, and addressing the instruction that it needs for calling it. And then this is just the exit message to make it look a bit nicer. Yeah, and then this here comes the actual instructions. So main, this loads the function definition in, and then stores the address at index 0 of it. This loads closures into it, and this isn't needed here. Oh, sorry. Oh yeah. Then this sets that. Yeah. Okay. This is this part's used for storing closures. And this here allocates some more memory, what's this called, and then calls main. So main is always renamed to main 0. Yeah. So then this jumps down here to main, creates a new scope, which basically just moves the stack pointer. Then it's just doing some arithmetic. Then it will set the return value, the return address. So $2 is the return register, and sets A equal to that. And then this is all. This is doing function calling and stores the previous function's return address and stack pointer, and then call jump return. Yeah, and then jump return. This returns back up to here, and then this will print the exit message and print the exit value. So all in all, yeah, so spim, take in the file out.asm, program exited with code 5, which is right. I'm just going to use a script which shortens it a little bit, so makes it easier. This is just a shell script. So okay, so mode is 1, and then okay, sorry, go to the next file, which is the branching / inputs / 2.c program exited code 5. Ooh. Oh, this one around. What am I doing? This is file directory. Oh, my bad. There you go. Yeah, so this is the attack outputted from this one. Oh, wrong one. Branch 1. Yeah, sorry, this is attack outputted from this one here. So it should output 100. Outputs 100 there. This is the attack for the code, and this is the assembly for this. I won't go through it all because it would take forever otherwise. Okay, then moving on to the next one, which is loop 2. This is significantly longer, this one now. But yeah, as you can see, oh, that is one thing I forgot to mention and why this won't exit is in my assembler and the attack and just in the compiler, I didn't have time to implement the break command, so this test fails because it won't exit. So that's a point I forgot to mention. A point that I made clear in my report, but I just forgot to mention now. It's one that doesn't have. Yeah, so just go to loop 1 instead. So a equals to 100,000. C equals to 1. A equals a minus c. Screen 1. Turns a. So a is equal to 1. And this is the assembly for that. Now moving on to factorial. So now my notice that the code, the assembly output is going to be significantly longer. As you see, this output is 362A00, and this is the code for it here. Now you can see here in the function definition there is another function here. This stores the address of the label factorial in function definition offset by 4 bytes. So this is the function factorial here. You can see here, and this here is the end label for the function. As I decided not to move the functions around or like set them all out, I left all the functions where they were or how they were in the source code. If a function definition is hit, it should be skipped. So this jumps from this jump here to L1. So this skips. So this is the end of function label. This jumps to L1 to. So this the reason for this will be coming through in just a second. Yeah. So this is just the factorial. This is the if statement here. Where is it? Yeah, branch if equal to 0. So this is the true part of the if statement, and this is the false part. This calls the function. So that is this part here, the else statement. It's a true statement. Okay, moving on to the next test. So this one is going to get significantly longer again. Let's skip 5. As you can see, outputs of code 3, as before. If I change this to 0 again, you can see it outputs 6. So, oops. The code for this is all of this here, and as you see this time in the function definition, there are many more. So all the functions are, every function that's defined in the source code is laid out here. As this is static, it doesn't change. So the address of the address of the instruction of any function can be found. Yeah, and then this is the get func. Then inside, this is what I mean by I didn't move any functions around. Inside the get func, this function here, there is a function definition here, and another function definition here. There's the one here. So they're not hoisted or moved around at all. They're just kept how they were. Yeah, so there's a lot of code and a lot of optimizations. If I had more time, there are quite a few. I didn't have time to make any real optimizations. Well, there's one or two, but I wasn't able to get around to doing optimizations with the using registers more instead of every temporary is stored in a memory location, where not every temporary really needs to be like that. In most cases, it wouldn't need to be stored. It can just be used. Just registers could be used instead, but I didn't have a chance to get around to doing that. And then finally, to make sure any changes that I made to the code didn't break something, another one, I created a script that runs pretty much all of the files in here, and each of them are paired with their expected output. So this basically compiles the interpreter and compiles the compiler, and then firstly runs the interpreter for a given test file, and then checks its output, and then runs the compiler given this, and then gives it the source code, and then uses spim to get the output from it, and then check it against the expected output that I defined up here. So and then this is Python 3. You can see this is the output, and all the test cases pass. And that is everything.